Hi, welcome to section 12.2. What I want to do today is we're going to talk about transforming data. We transformed data, right? We doubled things or added 10 to everything. We talked about if we could scale test results, sometimes your teachers just do +5 for everyone. Or sometimes teachers will double the score. So if it was originally a 30-point assessment, everything's gonna get doubled and scaled up to be a 60-point assessment, okay? We talked a lot about linear transformations way back when. So now what we're gonna do is we're gonna be talking about other kinds of transformations, right? So linear transformations is what I just described. If the variable to be transformed takes values that are 0 or negative, and we first applied a linear transformation to make sure all the values are positive, right? We usually add a constant to all observations, or we do something to work with them, okay? What we can't do is we can't straighten a curved relationship between two variables. So in chapter 12, we're really focusing on, scatter plots, linear regression, all those kinds of things. But what happens if it's not linear? Could we still use a line to describe the data? Right? So what's going to happen, and our key idea is we want to choose a power or a logarithmic transformation that's going to simplify our data by straightening the scatter plot. All right? We're going to take the variables, and then we're either going to take the data sets and maybe square the x's or square the y's or square roots or take the log of the x's or the log of the y's. I'll explain as we go through this lesson how we can tell the differences between them, okay, to work on getting our data from a curved data set to a straight data set. All right, so what we want to do, our first objective is we want to use transformations involving powers and roots to achieve linearity. We want to straighten our data using powers, raising stuff to exponents, and different roots as we work through. Your power law model is going to follow this format. So I rewrote it over here as it's y is equal to a number, right? You got your coefficient times your variable raised to a power. It's raising stuff to a power. The most common places you're going to see this, the words, the vocab that we're going to have in the problems, is it's going to be geometric relationships and biological scenarios. So geometric would be area, right? The area of a table, the area of a farm, the area of whatever it would be, because that's length times width or whatever it would be. So it's a squared dimension. And things that have volume, cube dimensions, okay? So volume can be like the volume of a person or the volume of an item or whatever it would be. And anything where we have relationships of living things, and because then they work together, okay? And we'll go through that as we talk about those different examples. So our first example would be here, okay? What does a country's mortality rate for children under 5 years of age per 1,000 live births tell us about the income per person measured in GDP per person adjusted for differences in purchasing power for residents of that country? So we've got our data set here, okay, of these different countries. And our original data, you will notice, is very curved. Okay, so we have a very curved data set. And one thing that I made a note about is that they're both one dimension, okay, or one dimensional. So it's not like something could be squared with area or cubed with volume. I'll show you those examples in a few moments. But if you've got both one dimension, then how you undo the one dimension is we look through these, right? So I made a note here that our original scatter plot shows a strong negative association, and it's clearly nonlinear. So the R value for this would be excellent. It would be like R equals -9 point something. If we plug these in, we don't need to plug these in a list, but if we did, our R would be really strong because this is a strong negative relationship, but it's not a linear relationship. And I made a note that since our X and Y axes are looking like asymptotes, then perhaps there's a reciprocal relationship, okay? Because if you have both of these, right, if your curve, if your axis was here and you had this, then we might be having a 1 over X or 1 over Y scenario that could explain how this data set would work together, okay, or how we could achieve linearity. So what we've got is I've provided to you guys two different transformations. All right, so commonly what you'll see is they're going to give you the transformed data, or they'll give you the equation of the transformed data. They're not going to just at this level, right, of Stats 101, you're not going to be asked to figure everything out from scratch. They're going to provide you some transformations, and you then need to maybe figure out what was the best transformation or make predictions using those transformations. So for our first transformation, and you'll notice a lot of times they give us the ordered pair. So here's the ordered pair. They're using under 5 instead of the word mortality. I wish I'd changed this when I copied your notes to say mortality, and this is our reciprocal of mortality. So this would be like 1 over the mortality rate. Okay, this transformation they did like a 1 over x comma y. They redid it. So they did the reciprocals of all of the x values in the original data set and put those reciprocals in as the x list and used the original y's. And they did the linear regression for that. So notice, see how it's straightened your data? It's a pretty linear relationship now, okay? When we're looking at this, here's the computer output. Transformation number 2 is saying this time they did the other as a reciprocal. So the mortality rate, the x's stayed the same, but the y became the reciprocal. So they did the reciprocal of all of the y values. Notice the y's went from, right, we've got like 38,000 here, and all these are in the thousands. Well, if you do 1 over these enormous numbers, you'll notice this y-axis, we have incredibly tiny decimals now, okay? So when they worked on that, this was like they said x comma 1 over y. So again, a lot of times you're going to be provided this kind of stuff, and we just need to then talk and work with them. All right, so the first thing is for this problem here, we want to do the following for both transformations. We want to find the equation of the least squares regression line for the first transformation and for the second transformation. Okay, so we know that it's y prime or y hat equals a plus bx. I like split this space so I could do transformation 1 on the left and transformation 2 on the right. Okay, and you'll notice what I've got is if it's a plus bx, if our ordered pair was back here, 1 over mortality comma income, then instead of the x, right, I got my a and my b here. These are my a and my b in this part of the computer output. So that's where this and this come from. But instead of x, the x variable was really 1 over mortality, and this was predicted income. All right. For the second transformation, we have very different numbers. We have our a and our b here. And remember, it was mortality rate, comma, 1 over income right here. So this time, our equation would be y hat equals a plus bx, where y hat is 1 over income. We've got the a and the b, and then we have mortality rate over here as a regular x because it was a regular x in the second transformation. All right, in the first transformation, the y was the regular and the x was the reciprocal. Okay, so that was it. We're just looking at what the equation is, because then for part B, we want to predict the income per person for Turkey, which had a child mortality rate of 20.3, which means we want to let x equal 20.3. So for the first one, we're going to plug in 20.3 right here. So we would get this. Our predicted income is 869 plus 104, 868 times 1 over 20.3, and we would get an expected income of about that. All right. Whereas for the second one, when we plug in the 20.3 here, we have to be careful because this is 1 over income. So this is all numerical. So just throw this in your calculator and you get this decimal. But we need it to be income. We can't have 1 over income. So if you have 1 over income as this, then we could also say that income is equal to 1 over that, right? Just using your property of proportions and reciprocals. So then when we look at this, right, you could just flip them both over because this could be like over 1. Or you could cross multiply, or however you want to look at it. So when you do 1 over this decimal, this is our answer. This is the expected income. So they're close to each other. These two answers are close because remember, these are approximations, and when you start manipulating data, then it also gets a little different as you kind of grow with it, okay? So it's not asking you like which is better, but we have two transformations, and now how do we work with those two transformations, okay? So if we take a look at example 2, okay, this is, we want to imagine that you've been put in charge of organizing a fishing tournament. Prizes are going to be given for the heaviest Atlantic Ocean rockfish caught. You know that many of the fish caught during the tournament will be measured and released. You're also aware that using delicate scales to try to weigh a fish that's flopping around in a moving boat will probably not yield very accurate results. It would be easier if you could measure the length of the fish while on the boat, and then you can predict its height, right, or its weight. What you need is a way to convert the length of the fish to its weight. Okay, so here is some data. We don't actually need to put our data in the calculator because it's already providing us our original data in our scatter plot. So clearly this is a strong relationship and positive, but it's curved, so linear is not good. Now, one thing we need to remember is that length is one dimension, right? You just measure it one way, so it's a one-dimensional thing. Weight can be thought of like volume, okay? It's 3D, it's cubed. It's that idea of weight or volume being 3D or cubed. So when we're looking at this data set, okay, they're giving us a transformation here, okay? So if we are given this transformation, this is transformation number 1, you'll notice a lot of times it's written in the axes, where if you have one thing that's one dimension and one thing that's the cubed dimension, we need to get them to be the same dimension, okay? So we need them to either both be cubes or both be 1D. So what they've done is instead of having length, right, which is 1D, and weight, which is 3D, this is the original. What they've done is they've done length to the third, so they've cubed the length. So if they cube the lengths for all of them, so they took all of these length values and cubed them, put them here, right now they're enormous data sets, like enormous numbers. It did a really good job of straightening out our data because we made them the same unit of measurement, right? In the same like three-dimensional concept. So if I forgot to put the equations down, but if the first thing I asked you was, what's the equation? Okay, well, we have our A and our B here. So be y prime, or y hat equals a plus bx, but be careful. It's weight is your y hat, x is length cubed. Oops, I'm off the screen, I'm sorry. So y hat is your weight, your predicted weight, but your x is length to the third power. So then if we say predict the weight of a rockfish that is 36 centimeters long, okay, you would need to plug in, right, it's going to be your predicted weight is 4.066 plus 0.0146774 times 36 cubed, because the ordered pair is length cubed comma weight. So you would plug this in your calculator with the cube part here, and we would get 688.9. Okay, and that would be our grams that we have. That would be our predicted weight. All right, so then if we look at the next guy, we have another transformation, okay? So this time, or actually before we even look at it, let's talk about it, right? So if you had to cube one to get them to both be 3D, well then if you want to bring them both down to 1D, the other transformation we could have done, right, is to cube root. So this way now they're both one-dimensional. This is one-dimensional, and weight was 3D, but if you cube root it, it brings it down to one dimension. Okay, and if you notice, it's also listed here in the axes, and it did a really lovely job of getting that straight as well. Okay, so when we're looking at that, let's do the same thing again. Okay, and you've got your ordered pair in your transformation. Commonly, that's also given to you that way. Okay, and as we take a look at this, first, guys, try writing out your equation on your own. Okay, and then we're also going to make that prediction for the rockfish. So we have y hat equals a plus bx, but when we plug in the variables, right? It's the predicted cube root of weight, and we've got these here with length as this as the x. So if we want to make our prediction for the weight of a 36 centimeter long fish, we would plug in the 36 here. The cube root of weight equals this. So then when you cube both sides, you're going to get just predicted weight of this to the third power. We're just doing a little algebra to solve it out, okay? And we would get our 697.85 grams. Okay, so those are examples of power models where you're raising them to a power, okay? When you take your variable, if we go back to the beginning when you wrote this, you've got your variable raised to a power. Okay, you could have a coefficient out front, you might not. It just kind of depends on the situation. And we can go through tons of those as we talk about them as well. So what I'd like to do next is I'd like to talk about our second objective, which is an exponential growth model. So when we're talking about things growing exponentially, right, we know usually it's exponential growth or exponential decay, depending on well, those are both growth in the negative direction, sorry, or it could go towards the x-axis for your exponential decay, getting closer and closer to zero. The big change in the format of its setup is it's a number, maybe you have a coefficient, but then it's a number to the variable power. Your variable is going to be up here as your exponent. When you've got logarithm transformations, okay, you're transforming, we're going to use logs or natural logs. You don't need to decide which is which, okay? It's going to be given to you in the types of problems. You'll see as you do the book work, whenever you get to the book work, you'll see also as we go through this first example right now, okay? One of the biggies, actually I'll just explain it as we cruise through, all right? But your exponential growth model right here, okay? If you've got y equals a times b to the x, it becomes linear when we plot the log of y against x. So I wrote here, if a variable grows exponentially, then its logarithm grows linearly. And it's just a common thing we can look at. You can either take the log of x or the log of y. They'll give you what it is. All right, so if we just take a look right here at example 3, Gordon Moore, one of the founders of Intel, predicted in 1965 the number of transistors on an integrated circuit chip would double every 18 months. This is Moore's law, one of the ways to measure the revolution in computing. Think about, wow, how much computers have changed since 1965, right? Here are the data on the dates and the number of transistors for Intel microprocessors. So this has absolutely grown exponentially. Okay, years since 1970, and the transistors, they're not being multiplied by a constant, they're growing in an exponential fashion. Right, so it would be a graph like this, back up here, it'd be just skyrocketing up. They're giving us a scatter plot of the natural log, okay, log base E, or the ln, of the number of transistors on a computer chip is shown below. So this x-axis is years since 1970, and this y-axis, I rewrote it because it was a little tough to read, is the ln of the transistors. So the natural log of these numbers. And it became really close to linear, okay? And I wrote here, so it's just saying, the question is saying, based on this graph, explain why it would be reasonable to use an exponential model to describe the relationship between the number of transistors and the years since 1970. So to describe that, an exponential model is good if your graph of that transformation is roughly linear. That's all you have to say. The same would apply if it asks you to describe why a power model would be applicable, and that would be if you're cube rooting or cubing or square rooting or squaring or doing the reciprocals like we did in those first two examples. Part B says a Minitab output from a linear regression analysis on the transformed data is shown below. Give the equation of the least squares regression line and be sure to define any variables we use. So we just want our y hat equals a plus bx. So we're going to grab our a and our b. I rewrote down here my ordered pairs, years since 1970, comma, the ln of the transistors. And what happens is we're going to have this equation, right? Y hat equals a plus bx. I'm going to plug in the y hat. This is my y variable. And then I'm going to plug in the x the years since 1970. Okay, so I just like to reorganize my thoughts with the ordered pair in the context of the problem, so that way I can cruise through the actual problem. All right, so we just have these two problems here to work on, and then we're gonna pause for today, and I will pick up with this two variables, like taking the log of two variables. We'll do that in class together. So what we want to do is we want to really look at like how we can work on this problem. How are we going to use our model from the previous page to predict the number of transistors on an Intel computer chip in 2020? So the first thing we need to do is we need to be careful, right? 2020 minus 1970 really means that we want when x equals 50. Okay, so we're not plugging in 2020 because it's always been years since 1970. So we knew that the ln, right, our equation, I'm just going to start up here because I didn't give you enough space. We have the ln of our transistors was equal to 7.0647 plus 0.36583 times x, which I'm going to put in as 50. Okay, these are all numerical, so you can just throw this whole right-hand side in your calculator, which means we're going to have that's equal to 25.3562. But we have to figure out how to get an answer, right? What are we trying to find? So I'm going to convert my ln. The ln of an amount is really log base E of transistors. Because now I can rewrite this. Remember, off to the side, maybe over here, if you have log base B of A equals C, you can rewrite that as the base raised to this as the exponent equals whatever you were taking the log of originally. That's a common log. This is as fancy as we're getting with logs, guys, okay? So if logs were a little sticky, this is all you needed to know, okay? And so that's why I rewrote this in this fashion, because I can take it and I could say, okay, well now it's going to be e to the 25.3562 power, and that's going to equal my number of transistors. All right, that's my predicted transistors. I've lost the hat up there. Okay, so here's my predicted transistors. I've got e to the, this is my exponent, this 25. So you're going to put this in your calculator, do e to this power. You should get this ridiculous answer. Okay, that, or it was like 1.028 times 10 to the 11 power. That's going to be your predicted transistors. Now, I know 2020 is in the past, so it's not really predicted anymore, but based on that data, we could have made that prediction before. Okay, so then just the last piece, part D, is saying here's a residual plot for the linear regression of the transformed data that we had. Discuss what this graph tells you about the appropriateness of the model. So with this, it's interesting because you can kind of see a pattern. So some students might say, well, wait a minute, this is a little off, right? Because you do have a pattern. But then you also need to look at the scale. And our scale goes from 1 to -1, or -1 to 1. That is incredibly tiny for how accurate your residuals would actually be based on that model, right? If we're talking about the original data were in the, millions and billions, right? Then being off a residual of 1 to -1 is pretty much nothing, okay? So I would write there is a pattern. But since the residuals are so small compared to the transformed y's, it's okay to use the model. All right, I know, I apologize, this was a longer video, I'm sorry, but it's probably our last video of the year. Hey, because this is the last section and we're going to teach this next part in class, so that's probably our last new lesson over video. Way to go, I hope you took awesome notes. Jot down whatever questions you have and I'll talk to you soon.